Ancient Egyptians sucked it out of the noses of their dead and then discarded it. Aristotle thought it was a radiator for cooling the blood. But by the end of the Middle Ages, the brain had won respect. No longer spurned as mere cranial stuffing, the brain was recognised as the seat of cognition, key to bodily function, a thing of intrigue, even beauty. In the 18th and 19th century, findings came thick and fast. Electricity's role in nerve function was spotted by Luigi Galvani, inspiring in a roundabout way Mary Shelley's Frankenstein. Louis Victor Le Bonnier helped show that different parts of the brain had different functions when he lost his ability to speak, but none of his other faculties, enabling Paul Broca to map brain areas that made speech possible. Santiago Ramon y Cajal showed that each spider-like brain cell was separate, not fused to its neighbour. That was key to understanding plasticity, and therefore the brain's ability to learn, remember, and recover. Come the 20th century, another patient, Henry Molaison, taught us about memory by losing his own on the operating table. The removal of parts of his brain to treat seizures left Molaison unable to remember new events, but still able to learn new physical skills, and allowed Brenda Milner to deduce that there are different types of memory located in different parts of the brain, which, give or take a few decades, brings us to now. Today, we have brain imaging technologies capable of eavesdropping on the ebbs and flows of brain activity from second to second, over distances just the breadth of a few human hairs, without harming a single brain cell. There are techniques like optogenetics that use light to control living brain cells, and transcranial magnetic stimulation that can speak to the brain in its own special language, rousing cells to fire or to rest, to meld into fresh circuits or go their separate ways. And all of this is coupled to insanely powerful computers capable of crunching the torrents of new brain data. International teams of scientists are jumping at the opportunity to use these tools to find out more about the brain. At the Human Connectome Project, they are mapping the brain's connections and relating those wiring diagrams back to each person's cognitive abilities, personality, and genetics. At the European Union's Human Brain Project, they are simulating the brain in a computer, arguably the only way to understand such a complex beast. At the US Brain Initiative, they are developing novel neurotechnologies to explore how brain cells and circuits interact in time and space. And at the Australian Research Council Centre of Excellence for Integrative Brain Function, we are working out how the brain interacts with the world, how it shifts attention to the things that matter, predicts what might happen next, and makes decisions continuously, subconsciously, and at breakneck speed.
Earlier in this module, we learned that much of our understanding of brain structure and function developed as a result of accidents. But what are the key brain structures, and which of these are critical for human learning? The human brain is very much an interconnected web of parts, but the three major areas are the cerebrum, the cerebellum, and the brainstem. The brainstem connects the brain with the spinal cord and controls biological processes like breathing, digestion, and heart rate. The cerebellum contributes to balance and motor control, but also to cognitive functions like language, attention, and regulating emotions like fear and pleasure. The cerebellum is also involved in procedural memory, which is the unconscious memory of skills and using objects like riding a bicycle. The cerebrum is the largest region in the brain and is divided into two hemispheres, left and right. There are symmetrical pairs of most of the key parts of the cerebrum in each hemisphere, such as the hippocampus and the temporal lobes. The neocortex is a sheet of neural tissue that covers the cerebrum and contains about 90% of the brain's neurons. The neocortex is critical to memory, attention, perceptual awareness, thought, language, and consciousness. The neocortex itself is divided into four regions or lobes across both hemispheres: the frontal lobe, the parietal lobe, the temporal lobe, and the occipital lobe. In terms of human learning, the frontal lobe, and particularly the prefrontal cortex, are important for decision-making and processing and retaining short and longer-term memories. The temporal lobe processes speech and vision and is also important to forming long-term memory. Inside the temporal lobe is a section that plays a role in declarative and episodic memory. Inside that is the limbic system. This includes the hippocampus and the amygdala, and many other organs which are associated with forming and processing memory. The hippocampus is critical to memory function, specifically transferring information from short to long-term memory. The amygdala is involved with processing and remembering emotional reactions. But these aren't totally localized, discrete functions. For example, both the cerebellum and the amygdala regulate emotion. Both the temporal lobe and the amygdala regulate the sense of smell. This illustrates the complex interconnectedness of the various brain structures.
The benefits of deep brain stimulation tend to be slightly different from one condition to another. Generally speaking, in well-selected patients, deep brain stimulation reduces the severity of their movement disorder, tends to improve their level of function, and generally allows patients to reduce their medication intake.
Aphasia refers to a disorder in the comprehension and/or expression of language. It's typically associated with a stroke, but can also occur secondary to trauma or a space-occupying lesion. So in this picture of the brain, Broca's area is in the frontal cortex and is responsible for language production. Broca's aphasia, therefore, is a form of expressive aphasia. There's no issue understanding speech, but when it comes to expressing speech, there's a struggle to form complete sentences. Classically, the patient will form abrupt one or two word sentences for what they want to say. The patients tend to have an awareness that they have this language difficulty, and so it can be frustrating for them to try and express what they want to say, knowing that they can't get the words out. Wernicke's area is in the temporal lobe and is responsible for language comprehension. So Wernicke's aphasia, that's a form of receptive aphasia, where there's difficulty in understanding speech. As well as that, they form complete grammatically sound sentences, but with jumbled up words that can be difficult to understand. And they tend to lack awareness that they do even have a language difficulty.
It's time for therapy, guys. Mirror therapy. Mirror therapy can be very effective in treating phantom limb pain. What is phantom limb pain? Well, if you're an amputee, you're probably familiar with this. It's when you feel like you have pain in the limb that is no longer there, what has been amputated. My ghost foot, if you will. I feel like I have someone stabbing my foot, or like there's an electrical wire hooked up to my toes, or like someone is peeling my skin. It's, fun things like that. There aren't super effective methods for dealing with phantom pain, which is a bummer. Generally speaking, it dissipates over time, but for some people, it lasts for months or years. I'm about 3.5 weeks in, and I am dealing with it a lot, especially in the evenings. So mirror therapy is one thing that has been proven effective. One thing to note is that it doesn't work immediately for most people. You have to work at it. You have to be consistent with it. I've been doing it every day ever since I got my cast off. Mirror therapy works by essentially tricking your brain into thinking that your amputated limb is still there, and you're able to move it and work with it and loosen it up, essentially. Your brain has a map of that limb that has been amputated, and that doesn't go away overnight. So your brain still thinks that your foot or your hand or your leg or your arm is still there. So this is what we do for mirror therapy. Now, I want to note real quick that I'm not a doctor, I'm not a physical therapist, I'm not an occupational therapist, I'm just an amputee who has learned a little bit about mirror therapy. So I'm just sharing my experience. Let's dive in. The first thing you're going to want for mirror therapy is obviously a mirror. Now, I'm going to show this for leg amputees, but if you're an arm amputee or another limb amputee, this can work for you. You just have to modify it. I start by sitting on the floor with a mirror in between my legs, and I put my head on the side of the mirror that my good limb, my intact limb, is on. Before we start, one thing to remember is that I am practicing these motions with both sides of my body. I'm trying to mirror these movements, and I am visualizing that side of my body as if it was fully there. So as I move my toes, as I move my ankle, I am trying to do so with the side of my body that has been amputated, even though it's not there, and I'm staring into the mirror at the side of my body that has been amputated and visualizing that it is still intact. So I'm going to begin by rocking my leg back and forth, and you can honestly begin by any kind of motion that you want. As we continue on, I might start moving my toe up and down, and notice that the whole time I'm looking in the mirror at the other side, at the reflection of my good leg, and I'm picturing the whole time that I have both legs. I may start making circles with my ankle, bigger circles, faster circles, slower circles. I might reverse the direction. Honestly, you can do any motion you want here. Personally, I have found that it's helpful to work up to different motions, so I kind of start off, like I said, by rocking back and forth, and then I'm working up to bigger or faster movements. You can kind of get creative with the movements you do here, but you want to make sure that everything you do is symmetrical. So it's always back and forth or circular. You never want to picture anything in the mirror or do anything that doesn't match what your leg is doing, what the reflection is doing.
Neuroplasticity is the ability of the brain to change continuously throughout an individual's life, resulting in changes like the alteration of gray matter in our brains, the regions responsible for concentration, emotions, impulse, sight, sound, memory, and speech. Although the developing brain exhibits a higher degree of plasticity, research has shown that the adult brain is not completely hardwired with fixed neuronal circuits. Neuroplasticity takes place through axonal sprouting, when the axons sprout new nerve endings in order to connect with other nerve cells to form new neural pathways. In order for the brain to be flexible, adaptable, and ready to learn, our brains need the compound BDNF, brain-derived neurotrophic factor. BDNF is a hormone responsible for neurogenesis, the creation of new neurons, and allows neurons to connect and combine into new networks, and thus plays an important role in neuroplasticity. The more BDNF available, the more neural network information can take place. You can increase BDNF levels in your brain and improve your neuroplasticity by simply lowering your sugar intake, getting enough sleep, and increasing your intake of certain nutrients important for aiding neuroplasticity. Ultimately, neuroplasticity allows us to evolve. Whether you want to squash bad habits or create new healthy ones, you must support healthy brain plasticity.
I would
ability to learn and get better at tasks through experience is part of being human. When we're born, we know almost nothing and can do almost nothing for ourselves. But soon, we're learning and becoming more capable every day. But did you know that computers can do the same? Machine learning brings together statistics and computer science to enable computers to learn how to do a given task without being programmed to do so. Just as your brain uses experience to improve at a task, so can computers. Say you need a computer that can tell the difference between a picture of a dog and a picture of a cat. You could begin by feeding it images and telling it, this one's a dog, that one's a cat. A computer programmed to learn will seek statistical patterns within the data that will enable it to recognise a cat or a dog in the future. It might figure out on its own that cats have shorter noses and that dogs come in a larger variety of sizes, and then represent that information numerically, organising it in space. But, crucially, it's the computer, not the programmer, that identifies those patterns and establishes the algorithm by which future data will be sorted. One example of a simple yet highly effective algorithm is to find the optimal line separating cats from dogs. When the computer sees a new picture, it checks which side of the line it falls on and then says either cat or dog. But of course there can be mistakes. The more data the computer receives, the more finely tuned its algorithm becomes, and the more accurate it can be in its predictions. Machine learning is already widely applied. It's the technology behind facial recognition, text and speech recognition, spam filters on your inbox, online shopping or viewing recommendations, credit card fraud detection, and so much more. At the University of Oxford, machine learning researchers are combining statistics and computer science to build algorithms that can solve more complex problems more efficiently, using less computing power. From medical diagnoses to social media, the potential of machine learning to transform our world is truly mind-blowing.